All right, good afternoon. Today, first of all, I just want to talk a little bit about what's going on. So you got your exam back. I know the scores were lower overall. I would encourage you not to get discouraged. Look over what you missed. Make sure you understand what you missed. Come by the office and get some help. You know, it doesn't have to be today. It can be Thursday. It can be next Tuesday or Thursday. But you want to address why you missed the problems because, you know, the final's coming up. And you don't want to get disengaged at this point because we only have 3 lectures after today. That is it. And then the final. And there's a lot of points still out there. Remember, this is a performance-based class, so a lot of your grade is based on your exam grade. So that final, you know, if you address what your weaknesses are and you understand what you missed and why you missed it, and you come through on that final, it's going to help you. Remember, they replace that first, you know, can replace your first grade, kind of like they did in 105 with your score on the final. So don't give up yet. The main thing is just really bust it out the next 3 weeks, and then you're done. And I know what this is like. I've been right where you are, and that's what you got to do. You got to work. You just got to, you know, it's about grit and determination and learning it and addressing your weaknesses, and that's what we're shooting for. So if you haven't come by the office, feel free to come by the office. We'll work through the problems, make sure you understand. If you can't come by the office, some people say they have something right after this class, then go to the Learning Center and get some help. But at least dialogue with somebody to find out what you're missing and why. The homework is due next Monday. Today, I'm just going to focus on Ksp. I was actually supposed to focus on Ksp and Lewis acids and bases. I just don't really want to mix the two together. And with the projectors the way they are, I think we'll just do Ksp today. That being said, Ksp is really important. And I think the very first part of this lecture is really important. If you don't get this part, this like first maybe half hour, 20 minutes of it, then you're going to struggle through the rest of it. So today you got to be concentrating on the lecture step by step. If you don't understand something, just yell out and I'll re-speak it, I'll restate it, or whatever it takes. But to me, this is a crucial part here. This is the last of our equilibrium constants called the solubility product constant. And I find that students don't do so well on this, but it's not because it's that difficult. It's because it's at the end of the semester. You just came off an exam. And if you had a weakness in equilibrium in the previous test, it's going to show up here as well. And so the other thing that makes this Ksp maybe a little bit more challenging, and it really comes back to 105 topics, and that is, do you know your polyatomic ions? If you don't know your polyatomic ions, go back to that memorization list in 107 and make sure you go through those with some flashcards and get down the names and the charges and so forth, because I find that just think about where we've seen polyatomic ions and where it maybe hurt you on the previous exams. If you don't know that phosphate is PO4 3 negative, then you don't know that you need 3 hydrogen ions to make phosphoric acid. If you don't know that phosphate's 3 negative and you combine it with sodium and it's Na3PO4, there's 3 sodiums for every 1 phosphate, then you wouldn't get the Van't Hoff factor right, because the Van't Hoff factor would be 4, 3 sodium ions and 1 phosphate ion. So that hurts you when we talked about freezing point depression or boiling point elevation or osmotic pressure. So one of the underlying things is that you have to know your polyatomic ions. And so that's why on this first slide, refresh your memory of polyatomic ions. It's under course details, exam info, concepts to memorize. Make sure you focus on those polyatomic ions. The other thing you probably want to refresh your memory on from Chemistry 105 is the solubility rules. It's on page 181 in chapter 4. I think it's so important. I actually went back and looked at the OpenStax book and found out what page it was. So that's telling you it's important that you know your solubility rules. So that's the pre-study before you even start Ksp. So if you have those solid, then you're ready to talk about this last equilibrium constant that we're going to cover, which is solubility product. And it's interesting stuff. This is, we use solubility product a lot. A lot of times we selectively precipitate certain ions out of solution. so that we can purify something. Like I just was at a talk last week, and they developed, in fact, Dr. Blue was on the research team that developed a compound that bonds with mercury and arsenic. And so in Bangladesh, they've got these large aquifers of water. People need water to drink, but the problem with the aquifer is it's got a lot of arsenic in it. So they made a substance here that when you pour the water through, the arsenic 3 positive ion binds with this substance, so it removes that part of the arsenic. So then it makes the water a little bit more drinkable, and then there's a couple more ions you have to get rid of, but it's a good start. And it also binds with mercury, and so the mercury, once it's bound, that's a good thing. It takes the mercury out of water or other what we would call industrial waste, and so it's not in people's drinking water. So interesting stuff that was developed here, and it's based on solubility. Will it bind and precipitate out? So we're going to talk about solubility product expression. And you go, what is that? Well, it's just like everything we've been talking about, equilibrium expression, right? You know how to write the equilibrium expression for any reaction. That's what and it's just called solubility product expression. Then Ksp, the solubility product. I mean, think about one of the overarching things in this class is equilibrium. We've talked about Kc, we've talked about Kp, we've talked about Ka, Kb, Kw, and now we have Ksp, the solubility product. So you know you're going to be multiplying something because I got the words product in there. So then we're going to do some calculations involving the solubility product and solubility. And here's the number one thing I find students get confused right off the bat, is they think solubility product and solubility mean the same thing. They do not. They do not, all right? Solubility product is an equilibrium constant. Solubility is how much substance will be dissolved in a certain amount of, how much solute will be dissolved in a certain amount of solvent at a given temperature. Now, from solubility, we can determine solubility product at particular temperatures, but just make sure solubility product and solubility are two different things. Yes, there's a relationship there, but make sure you understand those are two separate things. If you do that, you'll be more successful in this chapter than if you don't get that down without a doubt. And then we'll do a little bit of predicting precipitation reactions. When I pour lead nitrate into a beaker full of sodium chloride solution, does lead to chloride precipitate or not? That's what we're getting in on that last topic, predicting the precipitation reactions. All right, so the first thing is solubility is super important, and it is. Like I said, we use it to purify things. Your body uses it to purify your blood through your kidney. And if you have a precipitate in the kidney, you would call that a kidney stone. Most common kidney stone is a calcium oxalate stone, super painful. And it's when something this substance precipitates out into your kidney. And there are other types of kidney stones, but that's the most common one. Another place you see precipitation reaction is gout. I don't know if you've ever heard of somebody getting gout, but usually it's a precipitation reaction in the joints, and it's uric acid. Uric acid precipitating out. It's a yellow-looking substance, and it's painful too. So those are a couple of precipitation reactions in the human body. So industry, medicine, everyday life, there's precipitation reactions. And the compound, so here's what we didn't say in Chem 105. We said, remember those solubility rules? We said these things don't dissolve in water and these things do dissolve in water. Well, we weren't quite being truthful there. Even the insoluble things in chapter 4 in your book actually are very slightly soluble. So when somebody says, well, mercury 2 chloride is not soluble in water, yeah, it is. I wouldn't want to drink the water that's got mercury 2 chloride in it. Yeah, most of it's a solid precipitated in the bottom of glass, but there are going to be mercury ions in the solution. So when they say things are insoluble, there is going to be a certain amount of solubility. How are we going to determine that solubility? Generally, we look at the solubility product constant because that's the equilibrium constant. And what we know about K, which you saw in the exam, the larger K is, the more the reactions favors the forward reaction, that the products are favored over the reactants. All right? So larger K values, the products are favored over the reactants. That's how we get a large K value. So same thing with solubility product. The higher the solubility product, the more likely the substance will dissolve in water. So let's look at a common one here, and that is silver chloride. So this is why you have to go back to Chapter 4 and look at those solubility rules. So the solubility rules said that all bromides, chlorides, and iodides are water soluble except when they're attached to silver ions, mercury ions, or lead ions. So here we have silver bonded with the chloride ion. So silver chloride is a precipitate. So if I had a glass of sodium chloride solution and I poured some silver nitrate solution in it, remember all nitrates are water soluble, the silver ion would bind with the chloride ion and form the precipitate silver chloride. So there it is. It's a solid. You go, man, I don't remember that. That's why you got to go back and look at those solubility rules. If you don't get that down, this isn't going to be very helpful. So here we have the solid silver chloride, and some of it, we said it doesn't dissolve, but in reality, some of it does dissolve in water. And when it dissolves, it forms the silver ion. And we know this is dissolved because it says aqueous. And we have the chloride ion, and that also we know dissolves because it says aqueous. We also know that this can form an equilibrium between the solid and the ions. In fact, the equilibrium between the solid silver chloride and its ions, we call that a saturated solution, right? When you've added so much silver chloride, it's piled up in the bottom of the glass, and there's silver ions and chloride ions in the solution. There's an equilibrium there between the silver chloride dissolving and the silver chloride precipitating back as the solid. So these are things we already know. And so we write the equilibrium expression for this reaction, and you would say K equals the products over the reactant. But hey, the reactant's a pure solid. The pure solid doesn't change appreciably. As long as there's a little bit of solid present, this equilibrium can be established. And since the concentration of the silver chloride does not change appreciably through the course of the reaction, it's actually integrated into the equilibrium constant. So, because we're talking about solubility, we don't just call it the equilibrium constant, we call it the solubility product constant. All right? So you got to speak the language of a chemist. Somebody asks you for the solubility product constant, they're asking you for the equilibrium constant for this precipitate. All right? That's what it means. Same thing here that we've learned previously, that the smaller K is, the less soluble the compound, because the smaller K, that means the products are not being formed, and so that means we're staying mostly on the left-hand side of this reaction as solid silver chloride. So the smaller the Ksp, the smaller the solubility product, the less likely this reaction goes in the forward direction. All right. This slide is so important. I put the colors of yellow and this blue in here because this is where I find, okay, let's say you've got your polyatomic ions down, you've got the solubility rules down. This is the next real big hang-up, and that is molar solubility and solubility. So molar solubility means how many moles of solute. In the case of the silver chloride, it would be silver chloride dissolves in a liter of solution. So it is a concentration, it's moles per liter, it's molarity, but we call it molar solubility. And the thing about molar solubility or solubility, it is temperature dependent, so you must know what the temperature is. And generally as the temperature goes up, solubility goes up as well, and that is why in hot tea, you can put lots of sugar in hot tea and it'll dissolve, but you try to dump a lot of sugar in a glass of iced tea, all that sugar sinks to the bottom because you've saturated the solution. So molar solubility has moles per liter. Solubility, which is the most common outside of chemistry, solubility is probably the most common term. That is the grams of solute per liter of saturated solution. And you go, why is this the most common term? Because I don't have to know what the chemical formula of the substance is. All I have to do is weigh it out, know the grams that I have, and know how many grams dissolves in a liter of solution, and I'm done. So for chemists, we love molar solubility because we know moles backwards and forwards, and we know molar mass backwards and forwards. But outside of chemistry, solubility probably rules the day. Now, usually, these concentrations are at a temperature of 25 degrees Celsius. If you look at a table, they're almost always at room temperature. That's what we're most interested in. All right, so how do you calculate molar solubility from the solubility product? All right? How do you calculate molar solubility from the solubility product? And you ought to be going, oh, this is an ice table. This is what we've been doing. K is like Ka, and molar solubilities is how much of silver ion and chloride ion do I have present at equilibrium. So it is ice table. That's not the new stuff here. You understand ice tables. If you don't, that's what you got to get help on. But ice tables at this point ought to be automatic for you. So you construct an equilibrium table, which we've been calling an ice table. Fill out what we know, figure out what we don't know. All right, so that's the procedure. It's ice table. So here we have it. We have the solubility product of silver bromide. Again, according to the solubility rules, bromides are always water soluble except when they're attached to silver, mercury, or lead. Here we have it attached bromide to silver, so it's not very soluble. Look at that solubility. 7.7 times 10 to the negative 13. It's a really low solubility. And that's why we said in 105 this stuff doesn't dissolve in water. Well, in reality, yeah, a little bit of it does. Very, very, look, it's 7.7 times 10 to the negative 13th. That's the equilibrium constant. That's the solubility product constant. You know when you see a K that small, this reaction is not going in the forward direction. That the reactant is going to be much more, and it's not really a reactant. This isn't really a chemical. Let's make sure we know this too. This is not a chemical reaction. This is not a chemical reaction. Silver bromide was an ionic compound to begin with. It's still silver and bromide over here. It's still ionic. So we're just looking at processes here. So I shouldn't use the word chemical reaction. It's not a reaction. It's a process. So let S be your molar solubility, moles per liter. That's what it was in the ice table when we did Ka. It was an X, and it stood for the concentration of the hydrogen ion in its conjugate base. So here, instead of saying X, we use an S to stand for solubility. So this is what you know. You start off with a certain amount of silver bromide, and you have 0 of the silver ion and 0 of the bromide ion initially. So you've got a glass of water that you know the volume, you've dumped in the silver bromide, and the reason why we have blanks here is because it doesn't matter what the concentration of the silver bromide is, as long as you have some present, it's there. We don't, it's a solid. It's not part of the equilibrium expression, right? So that's why they have these little dashes here. But initially you have 0 silver ion and 0 bromide ion. So you know that the first thing you do here, which we've talked about over and over, is you calculate Q, the reaction quotient. So reaction quotient is really important in this section. That's why I never let go of it when we talked about it in the previous test. Some people said, I didn't talk about Q that much. Well, I did because Q is important for any equilibrium expression. So what does Q equal? Q equals 0. If Q equals 0, which it does, Q is less than K, so we know the reaction's going in a forward direction. And so knowing it goes in a forward direction, we're going to gain the molar solubility of silver ion, and we're going to gain the molar solubility of the bromide ion. So instead of saying plus X, and if you don't like S, you can say X. I don't care. But I usually put an S there to say, hey, we're talking about solubility here. So it's plus S and plus S. That's the change. If we add these all together, it doesn't matter what the silver bromide is because it's a solid. The equilibrium amount for silver ion is going to be S, and the equilibrium amount for the bromide ion is going to be S. All right, so it's a nice table. We know how to do that. So here's what you know about it too. You know that the equilibrium expression, called the solubility product expression, is equal to Ksp equals the two products, silver ion and bromide ion. The brackets being, remember, the concentrations have to be in moles per liter. We don't know what the silver ion is at equilibrium. We don't know what the bromide ion is at equilibrium. All we know is they're S. They're both S here. But we know S times S gives us S squared. So S squared is equal to the solubility product that was given, 7.7 times 10 to the negative 13. And we're going to solve for S, so we take the square root of 7.7 times 10 to the negative 13, and we get 8.8 times 10 to the negative 7th molar. That is the molar solubility of silver bromide. All right? That is the molar solubility of silver bromide. Now, what's the relationship between molar solubility and solubility product? If we take this number, 8.8 times 10 to the negative 7th molar silver ion, and we take 8.8 times 10 to the negative 7th molar bromide ion, we multiply those two numbers together, you will get this number, 7.7 times 10 to the negative 13th. So that's the relationship between molar solubility and solubility product. You have to have the expression, you find the molar solubility, plug that molar solubility into the expression, and you can then find out the solubility product. But in this problem, we're given the solubility product, and we're asked to find the molar solubility. So you're going to be expected to do that in your homework and on the exam. All right, questions so far on what we've covered? Anybody just totally lost? This is easy stuff if you follow it like this. It's just like, it's real easy, but you got to know it from the beginning, and that's why we're slow walking through this, because I want everybody to get this right. This is the reason why I want you to get this right. I think the next topic, the next chapter is a little harder, the electrochemistry. I'd rather make sure you can ace this. The electrochemistry, if you have problems with that delta G problem on the last exam, it's coming back. So delta G and that relationship in electrochemistry is coming back. And it's really important, the electrochemistry chapter, because any of you taking physics, that stuff comes back in physics as well. So you have, especially when we start talking about Coulombic charges and Faraday's law, and it's coming, and it's a little bit tougher topic. This still is related to everything we've been talking about, equilibrium constants. All right, so the molar solubility, because the relationship between silver ions and silver bromide is 1-to-1, that is the molar solubility of the silver bromide. That is the molar solubility of the silver bromide. 8.8 times 10 to the negative 7th. Now, like I said, outside of chemistry, a lot of times they don't want the molar solubility, they want the solubility. And the solubility has to have units of grams per liter. So all you have to do to convert molar solubility to solubility is remember the molar mass, or calculate the molar mass of silver bromide. So 1 mole of silver bromide, if you add it up on the periodic table, would equal 187.8 grams. So we put the 1 mole in the denominator, the grams in the numerator, the moles cancel each other out, and you'll be left with grams per liter, which is molar solubility. Just solubility, which is just solubility, all right? So solubility, grams per liter. And like I said, outside of chemistry, it's important. All right, let's look at another one. Now this one's a little more complex, and the reason why is because now it's not all 1-to-1 here. So here we have a common substance. I bet you've seen it in the lab, copper 2 hydroxide. It's a common lab that we do to have that precipitate out. It's kind of a white, bluish white substance. So we got copper 2 hydroxide, and you go, I don't know the chemical formula for copper 2 hydroxide. If you don't, you need to brush up on your naming, because that can hurt you on this exam too. We're at the end of General Chemistry 2, and they do expect you to know naming, and know that this Roman numeral stands for the charge on the copper. The copper is a 2 positive ion. Here's a polyatomic ion, OH negative. We've seen that over and over with the bases. So you got to have 2 of those for every 1 copper. So they want you to calculate the solubility, not the molar solubility, the solubility of copper 2 hydroxide. So how do you do it? Well, the first thing you do is you have to write a balanced chemical or a balanced equation. Let's just say equation. It's not really a chemical equation. It's just well, in a way, this went no. Almost, I can say we could. I still want to call it just a process here. All right. So we have copper 2 hydroxide. And it dissociates, that's the correct term, not dissolves, but dissociates. What dissociates means is they were already ions to begin with. All that's happening is they're separating. That's why we use the word dissociates. Whereas like with hydrochloric acid, when you add it to water or hydrogen chloride, it ionizes to hydrogen ions and chloride ions. So let's get the terminology right. It is dissociation. So copper 2 hydroxide becomes copper 2 positive ions. Aqueous means dissolved in water, and 2 hydroxide ions dissolved in water. So once you have a balanced chemical equation, the next step always is to write the expression. So here we're going to do the solubility product constant expression. Brackets mean moles per liter, so we got the copper 2 positive moles per liter, and then we have the hydroxide ion, and it's moles per liter. And don't forget the 2 here. The coefficient here is 2, so the hydroxide ion concentration is raised to the 2nd power. Those you starting to think about studying for the final exam, remember, don't confuse this when we did the kinetics, how we get those orders. That's what I find on the final is that students want to apply. This is easy, right? You look at that and put it right here, but remember, these orders can only be determined experimentally in a kinetics problem, so just keep that in mind. All right. Solubility product, constant for copper 2 hydroxide. This has to be given, so it wasn't given up here. It has to be given in order for you to solve this problem. Now, if they don't give it to you in the problem, that means you're going to be looking at a table. And on your sampling homework, you probably punch up something, and all of a sudden, all these solubility products come up, and you got to go find it. But in order to do this problem, you can't have 3 unknowns. You can have 2 unknowns. You can have these are related to each other, so that's really 1 unknown, and this is the other. Well, that means if I'm solving for this, I have to know the solubility product constant for copper 2 hydroxide. We look it up in a table. It's 2.2 times 10 to the negative 20th power. So this is less soluble than silver chloride. It does not want to dissolve. It does not want to dissociate. All right, so the other thing we need to do in order to solve this problem is they're asking you for the solubility, not the molar solubility. All right, so you got to calculate the molar mass of copper 2 hydroxide. So there it is, 97.57. All right, we set up an ice table like we've done over and over again. Initially, we don't care about the solid. It's going to remain as long as it's present, which it should. If we're going to get an equilibrium here, it's got to be present. This concentration is constant. That's why they have a dash here. Initially, the copper 2 positive is 0. The hydroxide ion is 0. But here's where it gets tricky. You got to go up here. For every 1 copper 2 hydroxide that dissolves, you get plus S for the copper 2 positive, but it's 2S for the hydroxide because of the coefficient 2 there. So if we add up the initial plus the change, there's our equilibrium values. We plug that into the expression, S for the copper 2 ion and 2S for the hydroxide ion, and remember that's squared. And so when you multiply this all out, you get 4S cubed. Now the most common mistake I see students make here, they come up with 4S squared for their value, and it's because they didn't multiply this squared term times the S here and make sure that's 4S cubed. This is the most common error right here. It's got to be 4S cubed. All right? So to solve for the solubility, you divide 2.2 times 10 to the negative 10th by 4. Take the cube root. And if you don't know how to do that on your calculator, you definitely need to know how to do that. You can use the y to the x key and 0.33 because it's the 3rd power, or you can find a cube root on your calculator. Some of them have it, some of them don't. So when we do that, we get 1.8 times 10 to the negative 7th molar. All right? So you come up here, and that's what this stands for. This is the copper ion. It's 1.8 times 10 to the negative 7th molar. That is the molar solubility. That is also the molar solubility of the copper 2 hydroxide, since it's 1:1. But that's not your answer. The answer, they asked you for the solubility. So if you stop right here, you have calculated the molar solubility. This problem asked you for the solubility. So to get the solubility, you take the molar solubility, multiply it by the molar mass of the copper 2 hydroxide. The moles cancel out, and we get grams per liter, and the molar solubility is 1.7 times 10 to the negative fifth. All right? So just read the question carefully. Is the question asking for solubility product, or is it asking for molar solubility, or is it asking for solubility? Read the question carefully, decide what you're trying to solve for. All right, so I'm not going to advance this one forward. Let's have you guys, it's already kind of, let's see if you can do this one on your own, though. Let's see how much of this you can draw up on your own. So they calculate the solubility of the calcium sulfate is found to be 0.067 grams per liter. All right, the solubility. They're asking you for the solubility product. It's the reverse of what we've been doing, but I want to see if you can do this on your own before I show you the answer here. So that's what the question's asking for. Calculate the Ksp, the solubility product for calcium sulfate. Let's see if you can do it, and then we'll see where we're having problems. All right, let's look at this problem. So the first thing you have is calcium sulfate. And calcium sulfate, this is why you need to know the solubility rules. All sulfates are water soluble, except the lead, the mercury, and the silver, just like the chlorides, bromides, and iodides. But also barium, calcium, and strontium. So calcium sulfate is not very soluble. In fact, we said it's insoluble in Chem 105. So the calcium sulfate is a solid, and it's going to be in equilibrium with the calcium 2 positive ion, which would be aqueous, plus the sulfate ion, 2 negative ion, which is aqueous. And again, if you don't know your polyatomic ions, then sulfate, you don't know it's 2 negative. Maybe you don't. I bet everybody knows calcium's 2 positive, but there's a few probably that still forget that sulfate's 2 negative. And that's where you're going to get into trouble if you don't know your polyatomic ions. So once you have a balanced chemical equation, the next thing you want to do is you want to write the solubility product expression. Ksp equals the concentration of the calcium 2 positive ion times the sulfate ion. And again, the solid is integrated into the constant itself. So that's my solubility product expression. So the next thing is, and the reason why you want to do the solubility expression is that tells you what the players are. And the brackets tell you that those concentrations are in moles per liter. So ice table, doesn't matter what this is initially. This is initially 0. This is initially 0. Q is equal to 0 initially, so Q is less than K, so we know the reaction is going to go in the forward direction. And so that means we're going to gain plus S of the calcium ion and plus S of the sulfate ion. So if we add the initial plus the change, we get the equilibrium. This is positive S and this is positive S. And we're ready to plug those values into the solubility product. So the solubility product equals S times S, all right? And we know that the molar solubility, the solubility is equal to 0.67 grams per liter. And again, the advantage of this is I don't have to know what the chemical formula for calcium sulfate is as far as solubility goes. I just weigh it out and I find out that it's 0.67 grams per liter for the solubility. So here's the dilemma. This is in grams per liter. We're asked to solve for this, so that means these two things have to be known. These two things have to be known since we're asked to solve for that, and all we have is this. And then you got to recognize, oh, this is in brackets, and brackets mean it has to be in molarity units, moles per liter. So you look at this and you go, oh, it's not moles per liter, it's grams per liter. So we know over and over again to convert grams to moles, we need the molar mass of the substance. So we look up, we calculate the molar mass of the substance. It's 136.2 grams per 1 mole. And when we multiply this out, we get 4.9 times 10 to the negative 3 moles per liter, or molarity units for that's the molar solubility. So now we have S. We know what S is. We know it in the units of moles per liter. All we have to do is plug that in here. So really all we're going to be doing is squaring that term there. And so when we square that term, we get for an answer 2.4 times 10 to the negative 5th. All right? So 4.9 times 10 to the negative 3rd times 4.9 times 10 to the negative 3rd. It's that number squared, right? And we get 2.4 times 10 to the negative 5th, and that is the solubility product. All right, so solubility product for this is 2.4 times 10 to the negative 5th, and they say this is a relatively large solubility product. So keep that in mind. 10 to the negative 5th is considered a fairly large solubility product. Even though that value is small, and it does say that the reactants favored over the products, again, that number is fairly large for solubility product. All right, questions on that one? These aren't that hard, but you just got to kind of go through it, methodically, and if you do that. And the terminology, I think the terminology is really important. All right. Predicting precipitation reactions. This is even more important. I want to know when I add two substances together, will a precipitate form? This is really more important than, we've got to learn to walk before we can run, right? So this is what's going on here. So we're going to use the reaction quotient to predict when a precipitate will form. Q has the same form as Ksp. We already know that. Reaction quotient looks just like the reaction quotient expression and the solubility product constant expression look exactly the same. So that Q is non-equilibrium conditions and Ksp is equilibrium conditions. All right, so if we are not at equilibrium, the expression is Q equals the concentration of the silver ions and times the concentration of the chloride ions. Initially, that's what the I's stand for. You don't have to put the I's in there if you don't want to. They're emphasizing these are initial. So, if we calculate Q, and Q is less than K, if Q is less than K, we know the reaction goes in the forward direction. So let's go back to the dot cam there. All right, let's just use this one. Is that the one up there? Yeah. So, if Q is less than K, just like we had here, then we know this reaction is going in the forward direction and more is going to dissolve and no precipitate is going to form. All right? If Q is less than K, we haven't reached equilibrium between the solid and its ions, and so the reaction is going to go in the forward direction until Q equals K. Or Q equals or greater than K, right? Actually, it's got to be greater than K, actually. Technically, for the precipitate form, Q has to be greater than K. Because right at equilibrium, when Q is at Ksp, you are at equilibrium. And at equilibrium, you have a saturated solution. But at the point of saturation, it still looks like a clear solution. Nothing has precipitated out yet. All right? So if Q is less than or equal to the solubility product, no precipitate forms. If Q is greater than the solubility product, we know if Q is greater than K, the reaction goes in reverse, and the solid's going to form here, and you're going to form a precipitate. All right, so we're going to look through some examples here. Predict whether a precipitate will form when each of the following is added to 650 milliliters of 0.0080 molar, these different salts here. All right, so I guarantee you're going to have some homework problems that look like this, all right? So you have a solution of potassium sulfate. You're going to pour 250 milliliters of 0.0040 molar barium chloride in there. And the question is, will a precipitate form? So the first thing that you're going to have to do is you're going to have to write a chemical reaction. You're going to have to tell me potassium sulfate plus barium chloride, and you're going to have to tell me what the products are. All right? So the products from Chem 105, really, this is called a double replacement reaction. We're going to get the potassium chloride as a product, and then we're going to form barium sulfate as a product. Oops, I forgot the A there. Barium sulfate. You go, how am I supposed to know that? Well, here's how you know it from Chem 105. You know, according to the solubility rules, that potassium sulfate dissolves in water, and you have 2 potassium ions, aqueous, plus a sulfate ion, aqueous, and then you have barium ions, aqueous, and you have 2 chloride ions, aqueous. And you go, how am I supposed to know that? Because of the solubility rules. Then you know that the product is going to be, the barium is going to bind with the sulfate, and according to the solubility rules, that forms a solid. All right, that precipitates out. And then you know that for potassium chloride, to balance this, we need to put a 2 here. You get 2 potassium ions aqueous because that dissolves in water, plus 2 chloride ions aqueous because that dissolves in water. So you go, I don't remember this. Well, if you go back to 105, this was called the molecular equation. This is called the Ionic Equation, which actually tells you what's present in the solution. And can anybody tell me what the spectator ions are? Anybody remember spectator ions? That's right. Chlorine and potassium does not change from the reactant side to the product side. If you take those out, the overall net ionic equation is barium 2 positive plus sulfate 2 negative forms the precipitate barium sulfate. All right, solid. Now, you go, do I have to do all that? Well, it's good to do that. But what we're actually doing is, once we know the barium sulfate is formed, this is what we're interested in. There's going to be an equilibrium between barium sulfate solid and barium 2 positive aqueous and sulfate ion aqueous. Now we're into our chapter, Precipitation Ksp. So we know that the expression for this is the solubility product is equal to the concentration of the barium ion multiplied by the sulfate molar solubility. And so now we have the solubility product expression. And so what we need to find out is what are these concentrations initially. So we're actually finding out Q. And then we're going to compare it. So again, what's the difference? Q looks just like what we have for the equilibrium. But if you want to put a little I there like they did for those, we want to know what it is initially. All right. So they give us Ksp. They tell us you have to find that in the table. It should be given in the problem if you don't have a table. But if you may, for your homework, you may have to look that up in the table. So the solubility product for barium sulfate is 1.1 times 10 to the negative 10th. We have to calculate Q. Based on what we have up there, we have to calculate Q. All right, so for the sulfate ion, initially, you're going to multiply 650 milliliters times 0.0080 molar. And you can find out the millimoles if you want to do that, or you can do moles. I don't care which way you want to do it. Let's see what the way they want to do it so we can just follow theirs. But you need to find out what are the concentrations of the sulfate ion and the barium ion. So let's look at it. So for the barium ion, you added 250 milliliters of 0.0040 molar. Now, most students do that part correctly. They multiply those two things, and that gives you the millimoles of barium ion. Here's where most people make a mistake. This bracket means it has to be in concentration units of moles per liter or millimoles per milliliter. And the denominator is the total volume. And that's where most students make a mistake because they either use the 650 here or they use the 250. But you've got to add these two things together. You have poured this solution into a beaker of potassium sulfate, and the volume has increased, so the total volume is 650 plus the 250. So don't forget to do that part right there. That's the most common mistake. Now you're going to have, when you multiply the numerator, you get the millimoles of barium ion divided by the milliliters of solution, and we find out that the molarity is 0.0011 molar with respect to the barium 2 positive ion. Now, for the sulfate ion, we go back. Let's just refresh your memory what's going on here. Whatever the concentration of this salt is, it's a 1-to-1 relationship between the entire salt and how much sulfate you have. So you have to look at that. That's a common mistake there too. Because if we were looking at potassium ion, it would be twice that concentration, right? Because there's 2 moles of potassium for every 1 mole potassium sulfate. But for this, for every 1 mole potassium sulfate, you have 1 mole sulfate ion. So you multiply the concentration of the potassium sulfate times the volume of the solution, of the potassium sulfate solution. That gives you the millimoles of sulfate ion. And then you have to divide by the total volume. So that's what you see here. 650 milliliters of potassium sulfate multiplied by its concentration gives you the millimoles of sulfate, and then you got to divide that by the total new volume, 650 plus the 250 you added. And we find out that the concentration of the sulfate ion is 0.0058. Now notice, we're not worried about the potassium ion, we're not worried about the chloride ion. Those are spectator ions. They are not part of the expression. That's why we're not worried about them. So don't worry about the potassium ion or the sulfate ion. That's why it's good to pick out those spectator ions. So now we have the two concentrations, and we'll go from the PowerPoint here. And so we have the concentration of the barium ion, we have the concentration of the sulfate ion. There's nothing squared here or anything like that. So we just bring those down, multiply those together, and we get a Q equal to 6.4 we get a Q equal to, the reaction quotient is 6.4 times 10 to the negative 6. We compare that to K. Well, Q, 6.4 times 10 to the negative 6, is greater than K. And if Q is greater than K, the precipitate will form. So barium sulfate will precipitate out. So you say, what does this look like? You've got a clear colorless solution. It looks just like a glass of water. You took your barium chloride solution. Was it chloride? Yeah, barium chloride solution. Make sure that's right. All right, barium chloride solution. You pour the barium chloride solution into the potassium sulfate solution. All of a sudden, this looks like a glass of milk. Looks just like a glass of milk. In fact, that's probably where you see that reaction the first time as a kid. If you ever seen a magician say, I'm going to turn water into wine into milk, water to wine is just going from an acid solution to a base solution, so it looks pink and it looks like wine. And then you pour that solution into something like barium chloride, and the barium sulfate precipitates out and it looks like milk. All right? So that's what's going on here. You get a cloudy solution of barium sulfate because it did precipitate out. All right, let's have you do the second one on your own. All right, so same process. Now let's have you do the third one. Let's have you do C. So here's what you got. You've got a beaker. Inside this beaker, you have 650 milliliters of 0.0080 molar potassium sulfate. All right. Now, what you're going to pour into that is 325 milliliters of 0.25 molar strontium nitrate. All right, this is 0.25 molar. All right, so I want to know, will a precipitate form or not? And it does say assume the volumes are additive. Now, that is something to think about. You know, we teach in 105 that when you add two volumes of liquid together, it doesn't necessarily mean it's going to come out to be the sum of those two volumes. But we are going to make the assumption that sum is the same. The sum is they are additive. They're not. There's no solvent interactions or solute-solvent interactions. So I'm going to be looking for specific things here. As you do this problem, I'm going to go through the steps, and you should say, yeah, I did that step. Yes, I did that step. So we'll check through to see where everybody is. All right, let's start the process here. So the first thing I would do is I would just write the equation. I would say strontium nitrate, and that would be AQ, because all nitrates are water soluble according to the solubility rules. Reacts with potassium sulfate, and that's aqueous because all group 1A metal salts are water soluble. And then I'm running out of room, so I'll put my yield sign down here, and my yield sign says I should get strontium sulfate, and that would be the correct chemical formula for strontium sulfate because strontium's a 2 positive. Oops, I made a mistake right there. I see it now. There's a 2 there. All right. So nitrate's a -1 ion and strontium's a +2 ion. So sulfate's -2, strontium's +2. That is the correct chemical formula for strontium sulfate. And then you have to decide, is that water soluble or not? And what would you say? All right. So we know that that one's not water soluble, so we're going to put a solid here. And then the other substance formed is 2 moles of potassium nitrate. And you know anything with a group 1A salt or sodium ion is aqueous, that always dissolves in water. So there's my molecular equation. And if you can't get it from the molecular equation, then you're going to have to do the ionic equation. You are going to have to break that out and say this is strontium 2 positive aqueous plus 2 nitrate ions aqueous plus 2 potassium ions aqueous plus a sulfate ion aqueous. And then it's a double replacement. The strontium goes with the other negative ion sulfate, and the potassium goes with the nitrate, and you're going to get strontium sulfate solid plus 2 moles potassium ions plus 2 moles of nitrate ions. So everything it's ions here. I didn't put the aqueous with it, but that's what. So if you get stuck, that's what you have to do. All right. So write the balanced chemical equation and see what's going to react with what, and if you get stuck, then you may have to break out the ionic equation. But the bottom line is potassium and nitrate are your spectator ions. The overall net ionic reaction is strontium 2 positive reacts with sulfate 2 negative aqueous, and I'll put an AQ to AQ, and that forms the solid strontium sulfate. Now, once you know strontium sulfate, here's the problem. Strontium sulfate, solid, is going to form an equilibrium with the strontium 2 positive ion aqueous and the sulfate ion aqueous. All right? So that's what we're focused on, is just the precipitation. All right? So here, the next thing you're going to do is always write your solubility product expression. Ksp is equal to the concentration of the strontium 2 positive and the concentration of the sulfate 2 negative ion. And then you go, oh, I got to calculate Q, which is the strontium 2 positive ion times the sulfate ion. And these are initial concentrations. So the next thing you have to do is you have to figure out what those are. What are those molar solubilities for these two initially? So I'm not going to reinvent the wheel here. So here's what it looks like on the PowerPoint. You had 325 milliliters of 0.25 molar strontium nitrate. And so when we multiply the milliliters times the molarity, we get the millimoles of strontium ion. We divide that by our total new volume. We get 0.083 molar strontium ion. For the sulfate ion, you have 650 milliliters of potassium sulfate times the concentration of potassium sulfate. That gives you the millimoles of sulfate ion divided by the total new volume. We get a concentration of 0.0053 molar. All right? Plug those into your reaction quotient expression. That's the initial concentrations. We get Q equals 4.4 times 10 to the negative fourth. And then you have to compare that to the Ksp, which is 3.8 times 10 to the negative seventh. 4.4 times 10 to the negative seventh is greater than 3.8 times 10 to the negative seventh. So yes, the strontium sulfate will precipitate out. So had Q been less or equal to KSP, it would not precipitate out. But in this case, it's greater than KSP, so it does precipitate out. All right, questions on that one? Yeah. Now you're going to have to yell it out. Let's hear it. All right, do you have to convert the milliliters into liters? All right, let's talk about this one more time. You have to choose the way you are most comfortable. All right, that's the bottom line. And you might have saw that on the last test too. So for me, let's focus on the strontium 2 positive. What I'm doing here is this is 325 milliliters. And I multiply that by 0.25 molar, which I'm assuming is millimoles per milliliter. Now you can get away with that because that milli and that milli will cancel out or divide out, and you'll get moles per liter, which is molarity. And you go, why would you do that? Well, the milliliters cancel out. I'm left with millimoles of strontium ion here. And then in the denominator, I have 650 milliliters plus the 325 milliliters, and that gives me 975 milliliters. And so if I leave it in millimoles, when I take millimoles divided by milliliters, I get molarity, the capital M. Now, you have to be comfortable with that. If you don't like it, then I will tell you. You can convert this to 0.325 liters, multiply this by 0.25 moles per liter, and then you have to convert both of these milliliters into liters. I just think that takes a lot of time, and if you get comfortable with millimoles, let me just say it pays off in the long run. It's worth trying to do it, but I understand some people will not be comfortable with it, and that's okay. I don't care which way you do it, but you got to be consistent. But any of you guys thinking about taking quantitative analysis next, that is the class. You're going to be using millimoles per milliliter. They're not going to go through moles and liters there. They're going to go, because that's what the burette puts out, milliliters. It doesn't put out liters out of the burette, it's milliliters, so they just keep it in that range. All right? But choose which one you want to be consistent with. If you do that, you'll be fine. All right. Let's go on to the next topic, and that is the common ion effect, pH, and complex ion formation. So all of these things, and we're not going to do, let me just strike that. We're not talking about complex ion. So you can draw a line through the complex ion formation. We are not talking about that topic in this class. So common ion effect and pH, those do play a role. So here's what you know. You can add a lot of baking soda to water. Eventually the baking soda won't dissolve. So it sets at the bottom. You've saturated the solution. You've poured too much baking soda into the water, and that baking soda sinks to the bottom. It doesn't dissolve. Now, you pour some vinegar in that water. You pour an acid in that water. It's going to react with this hydrogen carbonate ion, and it's going to consume the hydrogen carbonate ion, and so more of the baking soda is going to dissolve. So pH can affect solubility. And so that's why that middle one there is going to be important. pH does affect solubility. So does the common ion effect. So let's talk about the common ion effect. We actually saw it. That's part of the buffer. That it's got the conjugate base there. So let's look at this common ion effect. What it is we started off with. Let's go back and see if I had this written down on. There you go. All right. Let me write it down. Let's do this. All right. So we go back to the equation we started today with, and that is silver chloride solid, and it forms an equilibrium with the silver ion aqueous, and then with the chloride ion aqueous. All right. We saw that at the beginning of class today. So we know that the solubility product for this Ksp is equal to the silver ion concentration times the chloride ion concentration. All right, so we know that. Now, if I asked you to find the molar solubility of silver chloride, you do an ice table, just like we did at the beginning of class. We'd have an S for the silver ion, S for the chloride ion. That gives us S squared. So S squared set equal to the solubility product of silver chloride. We find out the molar solubility of silver chloride is 1.3 times 10 to the negative fifth. All right, that's what we talked. That was the very first topic we did in class today. Now, what happens if some chloride ions already present? What if you added silver chloride to a solution that already had chloride ion present? Do you think more silver chloride would dissolve or less silver chloride would dissolve? Yeah, less, much less. Because you already got chloride ion present, you don't need much more silver ion to get to Ksp. So that's what the common ion effect is. If one of these two ions is already present initially, before you do any solubility calculation, then not as much is going to dissolve. All right, so we're going to see that. So it says determine the solubility. So let's go back to this. Let's focus on one thing here before we move on. The solubility of just silver chloride in water, the molar solubility is 1.3 times 10 to the negative fifth. All right, the molar solubility, keep that in mind, 1.3 times 10 to the negative fifth. That's just silver chloride in pure water. All right. Now, what happens? Determine the solubility of silver chloride in a solution already containing a solute that has the common ion, a common ion with silver chloride. So like the chloride ion, all right? So for example, well, they actually did the opposite one. So for example, consider dissolving silver chloride in a 0.1 molar solution of silver nitrate. So silver nitrate dissolves completely in water because we just said, according to the solubility rules from chapter 4, all nitrates are water soluble. So the nitrate ion, so because this dissolves in water, the silver ion is not going to equal the chloride ion concentration. So if you go back over here, you already had silver ion present based on the silver nitrate solution. So the silver ion does not equal the chloride ion concentration. So the silver ion concentration initially will be 0.1 molar plus the silver contributed by the silver chloride itself. All right? So you had a 0.1 molar solution of silver nitrate. The concentration initially of the silver ion is 0.1 molar. And when we get to equilibrium, it's going to be 0.1 plus the concentration contributed by the silver chloride. So the common ion here is the silver ion. So watch what happens here. You have the solubility product constant, 1.6 times 10 to the negative 10th. The silver ion isn't S. It is 0.10 plus S. It's the 0.10 that you had initially from the silver nitrate plus the S that's going to be contributed by the silver chloride. So we got 0.10 plus S. And then the chloride ion is just S. So here's what we can do. This is what's nice. So here you're going, oh, I'm going to get a quadratic. I'm going to get 0.10 S plus S squared, and then I get into a quadratic. No. We assume this S is negligible, right? When you got a number that small, the amount of change in solubility is going to be negligible compared to the initial concentration. So we're going to simplify this and just say that's 0.10 times S. So now we have 1.6 times 10 to the negative 10th, the solubility product of silver chloride equals 0.10 times S. We solve for S and we get S equals 1.6 times 10 to the negative 9th. So the solubility of silver chloride in a 0.1 molar silver nitrate solution is 1.6 times 10 to the negative 9th molar. All right, let's go back. If it was just pure silver chloride, the solubility was 1.3 times 10 to the negative 5th molar. So by adding 0.1 molar silver nitrate, the solubility has decreased by more than 10 to the 4th power, which is 10,000 times. So silver chloride, trying to dissolve silver chloride in a 0.1 molar silver nitrate solution, decreased the solubility of the silver chloride by 10,000 times. That's how powerful the common ion is, the common ion effect. If one of the ions present in the expression is already present at the initial part of the reaction, it's going to limit the solubility of the solvent. All right? let's have you guys, well, we'll just do this one. We don't run out of time. So let's just do this one. This is just giving you another shot at. Calculate the molar solubility of silver chloride in solution that is 6.5 times 10 to the negative 3 molar in silver nitrate. All right. So here's what you got to do. You look at the first substance, silver chloride, you go, that's my solid. That's my solid, and I write the equation for it. So that's what they did here. Next, you write the solubility product expression. We've got that. Now, the initial concentration of the silver ion is 6.5 times 10 to the negative 3. Normally it's 0, but because we had silver 6.5 times 10 to the negative 3 molar silver nitrate solution, the initial concentration of the common ion silver is 6.5 times 10 to the negative 3. Now, remember when you calculate Q here, Q is equal to 0, so the reaction is going to go in the forward direction because 6.5 times 10 to the negative 3 times 0 is 0. So Q is less than K. The reaction is going to go in the forward direction. We're going to get plus S of the silver ion plus S of the chloride ion. We add these together and we get this for our equilibrium values. All right, we plug that into the expression. We assume this S is negligible compared to the initial concentration of the silver ion. So we get the same thing. 6.5 times 10 to the negative 3, that's the initial concentration of the silver ion, times S, the concentration of the chloride ion, equals the solubility product here. We solve for S, we get 2.5 times 10 to the negative 8 molar. S is the solubility of the silver chloride, and notice it's less. It's 2.5 times 10 to the negative 8th, compared to, let's go back and compared to pure silver chloride solution, which was 1.3 times 10 to the negative 5th, compared to the solution that had 0.1 molar concentration of the silver ion, which is 1.6 times 10 to the negative 9th. For this particular reaction, where we have 6.5 times 10 to the negative 3, the concentration is 2.5 times 10 to the negative 8th. All right, let's see, what time is it? Now, let me give you this let me go through this one, because you got homework with this, and you do need to start the homework now, and then you'll finish the rest of it after Thursday. So this one I just want to point out, the reason why, and we'll go through some more of this, but the thing I want to point out here is pH does affect solubility. And it affects solubility pretty much the same way as what we see here. If this hydroxide, so magnesium hydroxide is a solid, and it dissolves into, or dissociates into magnesium ions and hydroxide ions. So OH determines pH, right? OH negative. So if OH is already present initially, this reaction is not going to go in the forward direction as far. It's not going to go this way because we already have some of this present. Or if we add an acid and the acid attacks the hydroxide ion, then there's less hydroxide ion to begin with, and so this reacts kind of like Le Chatelier's principle, right? If we remove this, the reaction is going to shift in a forward direction to make up for the loss of the hydroxide ion. And the way we see it as, the magnesium hydroxide is going to dissolve more. All right? So normally for magnesium hydroxide, this is what the calculation would look like for the solubility. You'd get 1.4 times 10 to the negative 4th. That's just pure magnesium hydroxide in water. But if you add an acid or you add an acid or add a base, it's going to affect that. So here what we did was they just want to know what the pH is. Once you know what the solubility of this is, you can, or the amount you have, you can take the negative log, get the POH, subtract that from 14, find out what the pH of the solution is. All right, we'll stop here today. I'll pick up on solubility and pH on Thursday, and we'll finish this part, and we will definitely finish Lewis acids and bases, and that's what you need to finish the homework on Monday.